Okay, maybe let's slowly start the session. Is everyone, are enough people inside? I think so. Yeah. So we start this morning session. I'll be the chair of the session. There are 2 talks before the coffee break, and after the coffee break there will be actually 3 talks. There's the talk of Maurice that was not given yesterday, right? So he's giving it today. That will be the last talk before lunch, okay? So we start the day with George Trainings, and he will talk about memory matters for quantum nuclei metals. And George has done his undergrad and PhD in Cambridge in the UK. Afterwards, he went for a postdoc at ETH in Zurich for quite a few years. And then now he's a postdoc in my group in Hamburg, and he has a Humboldt Fellowship, which is a very prestigious fellowship, to be there in the group. And we're excited to hear what George has to say.
Thank you very much, Mariana. And thank you especially for giving me the opportunity to speak here. It's really great to go to Brazil. It's insane. I love it. Yes, I wanted to follow the example of previous speakers and elaborate a little bit on my biography so far. I was too lazy to make an actual slide, but you'll just have to bear with me. And yes, at Cambridge, I worked with Stuart Althorpe on incorporating nuclear quantum effects into the vibrational dynamics of liquid water using path integrals. And then, indeed, I moved to ETH to work with Jeremy Richardson. The move happened just after the start of the pandemic, so that was fun, but maybe it's not for another time. The pertinent thing is that there I developed a theory of perturbative corrections to non-adiabatic reaction rates, calculated with golden rule instantons. Keywords. And with Mariana, I'm sort of continuing this theme now of looking how nuclear quantum effects and non-adiabaticity affect the properties of matter, hopefully in a way that we can actually simulate on a computer within a reasonable amount of time. Why do we care about non-adiabatic effects? We've had lots of excellent talks, which sensibly made the Born-Oppenheimer approximation, and we know that there's a lot of chemistry and physics that can be described in terms of a single potential energy surface. At the same time, when we take a bit of a closer look at things like bond-breaking reactions, especially reactions that involve some sort of charge transfer, you find that multiple electronic states can contribute to such a process and interact dynamically with the nuclear motion in non-trivial ways. Excellent examples of that appear in water-splitting reactions that were mentioned yesterday, and hydrogen evolution reaction, etc., etc. And another interesting example is the diffusion of particles on conducting interfaces. In Robert Meissner's talk, there was mention of anomalous friction at graphene interfaces as compared to plain old graphite. And this too is something that you can explain if you recognize the fact that there are multiple electronic states involved. So let's have a bit of a closer look at how we might describe this computationally. The typical setup would be a calculation where you're keeping track of, and so of course this isn't really working, where you're keeping track of the positions of your atoms, as you do, but then alongside that you also have to take care of how the populations of different electronic states evolve in tandem with your nuclear dynamics. So this is not an easy calculation to do, and there are several approximate practical ways of following such non-adiabatic dynamics. A very well-known one is Ehrenfest dynamics, which accomplishes this simultaneous evolution. And in this approach, instead of the nuclei evolving on a single potential energy surface, such as that blue curve that I've labeled 0, the nuclei feel the forces from a weighted average of all of the Born-Oppenheimer energies. So there we have the absolute squares of the coefficients of the populations of the states, which change in time. And these ENs, these are the Born-Oppenheimer energies. If we only had a single state, a single population, this would reduce to Born-Oppenheimer dynamics. And then electrons, in turn, they feel the motion of the nuclei, and they, the first part of this equation is something that we all know and love. That's just the standard time-dependent Schrödinger equation for the electrons. But then we have an additional term that feeds back the motion of the nuclei into the electronic dynamics. You can use this to study energy transfer, and Hanabachi back there at the back of the audience is using that to examine how energy can flow between organic molecules and excited water molecules and so on. But as she will attest, this is not a very easy calculation to do. You typically need very small time steps. You have to be very clever in order to make it work. And if you additionally want to examine these surfaces, these effects for materials, where you have something like a surface and you have a really large number of electronic states, you are, as they say, in a bit of a pickle. So, propagating electrons is expensive. How can we get around this? Well, we can look at there are many lessons to be learned from classical molecular dynamics simulations. We can employ coarse graining, which is to say, we can formulate the problem in certain regimes when the non-adiabatic coupling is not too strong, such that we don't need to propagate the dynamics of the electrons explicitly. We only look at the dynamics of the nuclei. It's just that the dynamics becomes a little bit more complicated. You will have to trust me, however, that this is much better than the equations I had on the previous slide. What we have here is a generalized Langevin equation. The generalized Langevin equation has some familiar characters. We have the force that you feel from the Born-Oppenheimer potential energy surface, but then you have a term over here that describes a friction that causes motion, causes velocities that are quite high to decrease. And in addition to that, you have some random thermal fluctuations over there. There are two important quantities that go into this equation. The first one is a drift vector, and this basically tells you how the strength of your friction varies with where your nucleus is. For atoms moving on metallic surfaces, for example, you can have a very wide range of behaviors for how the strength of the friction depends on position. Paolo Lazzaroni, that was a very English pronunciation. Paolo Lazzaroni has made a study of how the position dependence of friction can create a really unusual effects in the rates of chemical reactions that I will get back to in a couple of slides. The other component of the GLE is the memory kernel, this K, and this describes how your dissipative dynamics depends on the history of your system. So this is a little bit unusual. This equation of motion here is not a differential equation. It's an integral differential equation, which makes things a little bit harder. But in some cases, you can cheat a little bit. You can make a Markovian approximation. In the Markovian limit, the memory kernel reduces to a Dirac delta function. And in that case, your equation becomes an ordinary Langevin equation. Later in the afternoon, we will be running a tutorial on molecular dynamics with the package IPy, and there you will encounter the Langevin equation, where it's used for thermal sampling rather than to describe any actual physical dissipation. These quantities, the memory kernel, the drift vector, and so on, they can be computed ab initio, and it is something that you can obtain, for example, from the FHI Ames package. So, jolly good. We're done with non-adiabatic effects. What about nuclear quantum effects? Why do they matter in this picture? We are quite interested in studying reactive processes. Activated processes, of course, very strongly depend on things like barrier height, and I don't have to go into too much detail on how zero-point energy reduces the effective barrier height, and it can really change the calculated rates of reactions by an order of magnitude or so. Another important factor, especially as we start looking now at technologies that go closer and closer to ambient temperatures, operate under milder conditions, things like quantum nuclear tunneling also start playing an important role. And at some point, indeed, when you reach a sufficiently low temperature, a major reactive channel, a major contribution to a reaction rate will come not from thermally activated processes where your system, your nuclei go over the reaction barrier, but rather from processes where the system tunnels through. All this we want to include in our simulations, but well, we're not going to do it like this. We're not going to do this by calculating actual nuclear wave functions, because this is really a very, very complicated problem. It has appalling scaling, so what can we do instead? What we can do is we can turn to an alternative formulation of quantum mechanics, and we will start by looking at the quantum partition function. The stuff that I'm talking about, it takes place at thermal equilibrium, so this is quite a central quantity for us, and within the path integral formulation of quantum mechanics, we can express this as a path integral. Easy peasy lemon squeezy, problem solved. The path integral, what this thing tells you to do, is to consider the collection of all possible closed paths that live in imaginary time. That imaginary time is proportional to beta, to your reciprocal temperature. And then you are confronted with the simple task of summing the exponential of the action of all of these paths, and that gives you the quantum partition function without ever having to solve the Schrödinger equation. You can do it with continuous paths, like the one that I've drawn here, and this is the bread and butter of quantum field theory. We do not do quantum field theory. What we do instead is we discretize our paths. So we take our continuous imaginary time and we chop it up into equidistant segments. And if you do that, and later today we're going to derive it, if you do that, then this path integral expression for a quantum partition function looks exactly like a classical partition function, but for this larger system, for this ring polymer, where every slice of imaginary time, the circle, is a bead, and the beads are connected by harmonic springs. What the spring is comes directly from path integral theory, and this sort of thing we can sample very efficiently using molecular dynamics. So we can calculate quantum mechanical properties using purely classical techniques, and this scales much, much better than wave function-based approaches, needless to say. Just to drive the point home, using this quantum classical isomorphism, we can compute a lot of quantum properties by starting with our molecular system and then making a bunch of copies of that system. Each copy over here corresponds to a different bead on my schematic on the left. Then atoms in adjacent copies are connected together by harmonic springs. You do that for all of the atoms. And as you propagate as you sample the classical thermal ensemble for the system, you get quantum mechanics. And this is what was alluded to in the talk by Luana and in the talk by Mariana that we heard yesterday. So, using these tools, we can try and tackle what seems on the surface to be a very simple problem, that is the diffusion of a single hydrogen atom on the surface of copper. This really is quite a simple problem in the sense that it's quite well described by considering just the motion of the copper from its HCP adsorption site to the nearest neighbor side. We can pretty accurately describe this by mapping the multi-dimensional process on just this simple 1D potential. And we describe in a lot more detail how we converged everything, etc., in this paper that came out just last month. We have very good experimental data for the diffusion rates for this system that were measured at the Cavendish Labs in Cambridge in the group of John Ellis using this technique, a helium-3 surface spin echo. It's really cool. You know, you take spin polarized helium atoms and then you shoot them at the surface, and you can use the interference between the different spins to get the intermediate structure factor from which you can extract diffusion rates, and it's a technique that's really sensitive to processes that take place on the surface. So that's very nice. And then we have a bit of a problem because in their analysis, which we reproduced, modeling this process as classical and Markovian, reproduces experimental data really quite well, and this is worrying because we know that the temperatures at which this diffusion takes place, we're looking at 200 Kelvin for a very light atom in a fairly stiff potential and on a fairly stiff potential energy surface. This process should actually be pretty quantum, and it does not appear to be the case. So what's the reason? Well, to answer that, I first need to tell you how exactly one can combine the two components, the nuclear quantum effects and the friction, in a single unified framework suitable for practical calculations. So as I said before, quantum effects we can obtain in a very practical way by using the path integral formalism and mapping our system onto a ring polymer. To describe friction effects in a theoretically convenient way, we can replace the generalized Langevin equation with a harmonic path. And of course, here I don't have to go into too much detail about the Caldera-Leggett model, because you can just go down the road and ask at what was the Unicamp. Yeah. And ask Professor Caldera at Unicamp exactly how this Caldera-Leggett model works. The model was used to look at decoherence in Jefferson junctions, and early on, this was actually formulated. This was actually applied to this continuous path integral, continuous time path integral framework, which I'm not going to discuss, but you can put these two things together. You can put this mapping from a generalized Langevin equation onto a bath of harmonic oscillators, then ring polymerize this system plus bath of harmonic oscillators to get a ring polymer representation of a quantum dissipative system. I'm a little bit disingenuous with my plot here, because actually there are even more springs. All of the bath modes are connected into ring polymers as well, but when I was making that graphic, I ran out of springs when I got to that stage. So we'll stick with that. And this is a hefty calculation, Paolo will tell you. It's a really hefty calculation to run, with all of those extra copies and extra degrees of freedom, but you can do that. In quite an ambitious benchmarking study, Paolo Mariani and collaborators looked at some model systems where it was possible to calculate the exact quantum dissipative dynamics using wave function approaches. It's really something that you can only get away with in a few dimensions, but there you can actually compare how this approach how well exact methods are reproduced by this approach here, which is based on the quantum classical isomorphism for the partition function. And it works really well, which is great. And our task now was to apply this to a bit more of a real problem. But even though we mapped our hydrogen diffusion onto a one-dimensional potential, it is still very difficult to run this explicit bath calculation, and you definitely don't want to be doing that when you're studying real multidimensional atomistic processes. So what we're going to do is we're going to look at the progress so far. We went from a classical GLE to a harmonic bath to a ring polymer with a harmonic bath. In the last step, on the way to a practical method, we're going to do the reverse of this process. We're going to integrate out the harmonic bath to get a ring polymer generalized Langevin equation. This is what we derive in our paper. And one of the things that comes out when you integrate out the harmonic bath is that we renormalize the ring polymer springs. Before, the springs connecting adjacent atoms, adjacent beads, they were determined by, well, I mean, they're a simple expression that depends on temperature. However, when we turn on quantum dissipation, the strength of these springs changes, they become stiffer, and you also find that there are some interactions between non-adjacent beads. All of this works to pull the ring polymer together, and that has really important implications for reaction rates. If we look for a second at this sort of transition state theory picture, we can visualize a ring polymer transition state as something like this. You can imagine dragging your ring polymer to the top of a reaction barrier and constraining its center of mass there. What the ring polymer does is then it spreads over the top of the barrier, and how far it spreads depends on how stiff the springs are. The amount of this spread is directly related to how efficiently the system tunnels through the barrier. So, when quantum dissipation renormalizes the springs and makes them stiffer, it means that the ring polymer does not spread out as much, and this describes the suppression of quantum nuclear tunneling that arises as a consequence of dissipative dynamics. How much the degree of suppression actually depends on the details of the friction, and in particular on the memory kernel that I brought up on one of my very first slides. It is a bit of a technical detour. It is convenient in generalized Langevin dynamics to describe the memory of the friction, not in terms of the kernel itself, but in terms of its transform. In fact, this is also, this transform is also the raw data that you get from an FHI Ames calculation. When the friction is simple, when the friction is Markovian, the transform is flat. That's the green line. Real life is never as simple. If you calculate the friction kernel for our system, for hydrogen on copper ab initio, it turns out that it is actually quite non-Markovian in this energy range that is relevant to dissipation. And this will have implications to how much tunneling suppression happens in the system. Doing it this way is, as opposed to using an explicit bath, is really quite efficient because you of course get the same answer because my maths is right. But you don't have to sample a billion degrees of freedom in order to converge your calculation, and you get the same quantum transition state theory rate, but we're at only 1/10 of the simulation time. Fabulous. But I mentioned the keyword quantum transition state theory rate. This is not the end of the story. This is not the whole picture. The way you calculate rates in this ring polymer molecular dynamics approach is you split the rate up into two chunks, an easier chunk and a harder chunk. The easier chunk is the quantum transition state theory rate, which tells you essentially how likely the system is to be excited to the top of the barrier with thermal fluctuations, and then roll off it to go to the product. And this part of the rate is only affected by the standard conservative forces. This part of the calculation does not care about the dynamical effects of friction and thermal fluctuations. To get the full rate, however, you also need to ask the question, what exactly happens to the system after it's reached the top of the barrier? Because in the simplest scenario, once it reaches the top of the barrier, it can move on to form the product, and then you're done. But it can also recross. And this can have, and these effects we can account for numerically, and this can really, really change the rate compared to the transition state theory estimate. This part of the calculation does depend on the dissipative dynamics. So you really do have to tackle the problem of propagating the ring polymer generalized Langevin equation. And whereas originally, for the classical MD calculation, you only had one friction kernel, you duplicated your system a bunch of times. And for every new replica, you have a new kernel to worry about. But that's not a problem. It's also something that we have derived in our RPMD GLE theory, and you can express the different kinds of memory that you encounter in ring polymer generalized Langevin dynamics in a very simple way. So all you need to do really is to obtain the kernels and the drift vectors from an electronic structure calculation, and there is an easy recipe for upgrading the classical friction picture to the quantum mechanical domain. And we also have an efficient way of propagating the dynamics described by these friction kernels. And here is just a very, very simple sketch of how this quantity, kappa, which is the dynamical transmission coefficient, converges with the number of harmonic bath modes. In my sketches, I showed 4 harmonic bath modes, because otherwise I'd run out of space. But for the sort of memories that you encounter in the context of surface diffusion, you need many, many more modes to converge the memory effects. In this case, as many as 500. We use an approach that allows us to propagate the generalized Langevin equation much more directly, and that really, really cuts the simulation times and allows us to explore the long-time regime. Because ultimately, what this function, this dynamical transmission coefficient, gives you is its value at the plateau. This value here is what you use to multiply the quantum transition state theory estimate and obtain the final rate. The direct approach is much more stable, much nicer to use. I'm going to tell you what. So, going back to the title of my talk, I started by saying that memory matters for quantum nuclei on metal surfaces, even though memoryless classical nuclei seem to do the job okay. Well, let us first see what happens if into classical molecular dynamics we actually introduce the friction memory that we know has to be there from first principles calculations. And when we do that, it turns out that classical rates are now too low. You were wrong. Okay, and now what we can do is we can see what happens if into our calculations we include nuclear quantum effects without accounting for memory. And now the rates are too high. And that's because you have more zero-point energy. Okay, jolly good. The rates have accelerated, but they've gone up too much. So really, you need to combine the two things. And what you see that it is fortuitous cancellation of errors that gave these nice-looking classical results in the first place. But they don't have the correct physics. If we step aside and look at a bit of a broader temperature range, you see that ring polymer molecular dynamics correctly predicts this regime over here, where as the temperature on the x-axis goes down in this direction, your rates deviate from classical Markovian, from classical Arrhenius-like behavior and plateau into the deep tunneling regime. And you can see the onset of that in the experimental data as, you can check that, as the crosses within the experimental error start deviating upwards from a straight line fit. And this is something that we can capture with ring polymer molecular dynamics. This nicely brings me to my conclusions. And yes, so this was just the first demonstration of what we can accomplish with this ring polymer molecular dynamics, and we're combined with electronic friction. I hope you've internalized the message that both nuclear quantum effects and memory are important to get the physics right. We can do this very efficiently using ring polymer molecular dynamics, which is implemented in the IPI software package. We'll be introducing you to that package later this afternoon. Please come, it's gonna be great. Using electronic friction in RPMD, we can tackle a variety of processes, not limited to diffusion, but we can also try and study things like chemisorption, proton-coupled electron transfer, and the framework, this whole coarse graining approach, is extremely versatile. It's not limited to integrating out electronic degrees of freedom, and in the future, I think a very important step on bridging the gap between atomistic simulations and more mesoscopic approaches to simulating materials, we can use this to efficiently describe solvent effects, dissipation of energy to phonon modes, etc., etc. With this, I'd like to thank you for your attention and welcome any questions.
Thanks a lot, George, for this super clear and nice talk. So, questions?
Thank you for the very nice talk. It would be nice to have experimental data for lower temperatures. Is it hard to get?
Yes, it is hard to get in this particular case because what you have is an effect called islanding. So for hydrogen on copper, you have hydrogen atoms coming together into clusters. There are other systems, other substrates like ruthenium, for example, which actually, where you can actually see the deep tunneling regime much more clearly in the experimental data, and I think it's one of the systems that we'd like to tackle in the near future, and possibly already in full dimension, not just a one-dimensional model.
Hi, George. Very nice talk, very tutorial. And I really see, the quantum nuclei, I understand how they increase transition rates. I see the friction, how it basically decreases it. What is a hand-waving explanation for the memory? What is really the role?
Yes, very good. So that is, there are several aspects to it. In this particular example, the dominating effect from memory is the efficiency with which energy is dissipated as the hydrogen atom hops between different adsorption sites. This is an example of a low friction system, and in this case, the more efficient the energy dissipation, so the larger the friction, counterintuitively, the faster the reaction. In the Markovian case, because you have a flat, there we go, because you have a flat friction spectrum, the Markovian friction is equally good at dissipating motion on all timescales. A non-Markovian motion, which we've got ab initio, is not so good at dissipating energy for slower motion, and it is this slower motion that mostly contributes to the diffusive process. That's the dominating effect. Yeah, jolly good.
Any more questions? Or Christian wants to follow up? No. Any more questions from the students?
My question is about I think the last or the second to the last one.
Yes, of course. Something like that?
Yes. As I understood, this hydrogen escape rates is for the system where you study the diffusion on the surface of solid, right?
Yes.
Okay. Yes. My question has to do with if this would be applicable to lithium ions in this case, because this hydrogen is not an ion, right? It's a hydrogen.
Yes. It is a hydrogen atom, and in principle, you could use this framework to also simulate lithium ions. How much nuclear quantum effects you expect in that case is an interesting question, but of course you can do it so easily with RPMD. Why not?
So yeah, because in this case, I'm wondering how much this memory would change, because now we have an ionic particle, and maybe something may change a lot between the things. I'm thinking about electrolytes actually. If I could study the diffusion processes in lithium, when the lithium is trapped in the solvation shell and try to
Yes.
diffuse.
Absolutely. I mean, I think this is an example where the GLE framework would be very effectively applied to coarse grain the solvent and so on. And because you have a charged particle, it is very common in these situations to have quite strong position dependence and fairly strong memory dependence as well. It's typical when the environment interacts quite strongly with your system to get these non-Markovian effects. So my preliminary answer would be yes, you should think of memory.
And how costly is this calculation compared to the hydrogen? I mean, you have an estimation about that?
Yes, well, I think we can discuss a bit more of the details after, because there are two parts of to my answer. But yes, let's.
I'm sorry. Yeah. So just to add, I mean, the framework that George developed is really general for any process you can cast as a generalized Langevin equation. So any source of friction would be compatible with that. They would give rise to different kernels, different memories, and so on. But for example, even here, George was looking at friction coming from the electronic subsystem, so non-adiabatic effects. But you can also have friction just coming from other degrees of freedom of the solvent, for example. Yeah, and this is also somehow applicable to that.
So my question is about combining the two previous ones. So when we should expect these effects to be important, like when the electronic, like in metals, in light systems, and what is a rule of thumb when to worry about this?
Yes, excellent question. Excellent question. So for electronic friction on metal surfaces, a good rule of thumb about when that's going to be strong is related to the electronic density of states at the Fermi level. Generally speaking, the higher the density, the stronger you can expect the electronic friction to be. And also, the other thing is there are other sources of dissipation in that system. Hydrogen is very special when diffusing on metals because it does not couple very efficiently to lattice phonons, and as a result, the non-adiabatic dissipation channel becomes the most important one. So that's a bit of an answer.
Just by looking at this picture, it seems that when we include the memory effects, you basically don't change the slope, you don't change the barrier, but only the prefactor, right? You have a clear, simple explanation for that?
Yes, in this particular case, absolutely, because we are looking at rates that are a fair amount above the deep tunneling regime, where things even out. And because of that, when you include so I should also say the slope does not change appreciably between the non-Markovian and Markovian RPMD. There is a change, as you would expect from 0-point energy, between the classical and quantum rates. And the effect of memory here is mostly restricted to this recrossing to the dynamical transmission coefficient. So the plateau height exactly changes. So, and in this case, yeah, this is the behavior you would expect. Yeah.
I have a microphone here. Thank you. Well, very nice talk. It was very amazing. So I remember the you know the principle of Hamilton when you put some constraints, like virtual constraints, in a system, and then you tries to include these constraints to minimize the energy, and then this memory remembers me that principle that you solve the integral, and then you have everything included there, right? So I'm just trying to ask you if there is a way in which you can make maybe cheaper calculations, maybe trying to include these memory effects, even in the let's say quantum Markovian, sorry, classical plus memory, in the that in principle is too slow.
Oh yes, that's a wonderful question, and there is some work that has already been done in that direction, which is using non-equilibrium generalized Langevin equations for enhanced thermal sampling, and generally speaking, it is also a really interesting research question of whether we can formulate a good coarse grain theory of the ring polymer itself, where we look at the dynamics of the fluctuations of the ring polymer and coarse grain those away, so we are left with just the center of mass, which looks like a classical particle, but moving according to a special kind of GLE. This question is not something that's been solved, really, but there's some movement in that direction.
Nice, thank you.
More questions, or should we move on? So let's, we can do more in the coffee break. So let's thank George again and go to the next speaker. So the next speaker is setting up. It's Tariq Pereira Cisne. And I'm looking at your online information. So Tariq did his undergrad, master's, and PhD from the Federal University of Rio de Janeiro, UFRJ. And then he went for postdocs, I think at least one postdoc at the Federal Fluminense University, UF, where he's now as a professor. And I'm not sure you did more postdocs. I'm sorry for that. And let's see if it works. É o seu computador que tá? É? Deve ser a segunda tela só, então. Oi? É a outra tela, eu acho. Ó, e se você merece? E se você colocar... você duplicou a tela. Olha lá, tá vendo?
Ok.
Então tá... Entendeu? Você mudar lá pro outro lado.
Entendi. Tá bom.
Você deve dar aqui.
Tá bom.
Só daí você tem que fazer o modo apresentação. Isso.
Ok.
Yes, and he's going to speak today about orbitronics from transport to topology. So thank you.
Okay. First of all, thank you for the organizers for the invitation. I will. It's a little bit confusing because the configuration is modified, but I will do my best. So I will talk about a topic that has been focus of my research in the previous years. It deals with the transport and manipulation of electronic orbital angular momentum in solid-state systems. So I will dedicate some time to the introduction of the area, and many works we have done in our group will be out of this presentation. I will focus only in the essentials. So let me give an introduction. Here, a timeline, and everything begins with how many time ago in the famous experiment. Maybe the students do this experiment in laboratory classes, and the how experiment give you access to you put a metal under external magnetic field, and you let a current flow through this metal. You can observe a DDP between the sides of this metal, and it gives you access to the type of carriers, if they are electron or holes. It gives you access to the density of the carriers, and is a useful tool for these purposes. Later, Mott, in an experiment on nuclear physics, he considered an electron beam being scattered by a target made of heavy nucleus with high atomic number, and he showed that the electrons with spin up are scattered in one direction, and electrons with spin down are scattered in the other direction. Then Diakonov and Perel made a work considered similar situation, but in solids, where the whole of nucleus is played by impurities randomly distributed in your solid. In the turning of the century, Hirsch, this Argentinian physics, he discovered this effect, coined the term spin-Hall effect, proposed how to measure it, and a lot of phenomena related to the spin-Hall effect started to appear. The debate between the intrinsic and extrinsic contributions, the association with new topological phase of matter, and in 2005, these three guys here, Bernevig, Hughes, and Zhang, they wrote a paper proposing the existence of analogous effect to the spin-Hall effect, but that occurs in the orbital angular momentum sector of your theory. But the point is that this paper do not call any attention. For 10 years, people do not look very much for this paper up to 10 years ago. No, 5 years ago, that the interesting in the orbital Hall effect and topics related to the orbital Hall effect started to reappear. And in 2021, the first direct experimental observation of this effect was published in Nature, and many groups started to take serious this idea of orbitronics and orbital Hall effects and all these things related with electronic orbital angular momentum. So this area fits together with spintronics in our search for alternative ways to store and process information. Christian have shown the difficulties of miniaturization of your devices that generate some hotspots in your devices. So the point is that we cannot miniaturize the things as long as we want. At some point, we start to change the paradigm that we use to store and process information. And among the fields, orbitronics is closely related to spintronics, and I will make this parallel every time. So among alternative electronics, spintronics may be considered the most successful one. In the spintronics, you want to use the electronic spin to store and process information in a solid state device. To build a spintronic device, you must be able to execute 3 tasks. You must be able to perform spin injection in your device, spin manipulation, and spin detection. You may think crudely that you are writing information in the spin of electron, manipulating this information, and then reading the information. And preferably, this would be done purely by electrical means. And with this, I'm excluding the use of magnetic fields and magnetic materials. I'm dealing only with non-magnetic spintronics here. There is a problem with this. Electric field do not couple directly with the electronic spin. If you analyze microscopically your Hamiltonian, And this coupling must be intermediated by spin-orbit coupling. Is the coupling that intermediates the electronic spin and electric field. And this generates a problem. You must use atoms with high atomic numbers that are expensive, is not often found in nature. So this is the problem of non-magnetic spintronics. To build these devices, you may use some building blocks effects, some fundamental effects. The spin-Hall effect will be the focus of this presentation. In the spin-Hall effect allows you to generate spin currents and detect spin currents by the Onsager reciprocal effect, the inverse spin-Hall effect. The spin-Edelstein effect, I also work with Edelstein effect, but I will not talk about this. In Edelstein effect, you have a non-magnetic material that is non-centrosymmetric with some spin-orbit coupling. And if you apply a current in this material, your non-magnetic material acquire a non-equilibrium magnetization. It's not a current like in spin-Hall effect, it's a magnetization, is different. And you have also the spin-orbit torque. You have a non-magnetic material on top of a ferromagnetic material. You apply electric field. This generates a torque in your ferromagnetic material. So you can combine these effects to build spintronic devices that execute the tasks I mentioned previously. So the point is, we overcome the need of strong spin-orbit coupling to build our devices? And starting from the beginning, our crude view of the matter is composed by atoms. Atoms have electronic charge that can propagate in your solid. Usual electronic deals with manipulation of this electronic charge. The electron have a spin, a quantum mechanical spin, or you can see as a self-precession around the on-axis of the electron to keep the thing simple. And spintronics deals with the manipulation of the spin of electron, and the electron have the translational motion around the atomic nucleus. And the manipulation of this translational motion around the atomic nucleus is the issue of the orbitronics. So you can associate a Hall effect to each of these degree of freedom. So the Hall effect of usual electronics, you have a metal subjected to external magnetic field. You must break time reversal symmetry of your system in some way, and then you apply external magnetic field, and applying an in-plane electric field, this generates a transversal current, a charge current that accumulates at the edge of the sample, and you can measure by a DDP. This is the Hall effect. In the spin-Hall effect, it's not necessary to break time reversal symmetry. You can preserve the time reversal symmetry of your system, but you must have some type of spin-orbit coupling, or in the impurities on your material, or an intrinsic spin-orbit coupling in the band structure of your material, and then you apply electric field. This generates a transversal spin current that accumulates at the sides of your material, one side with spin up, the other side with spin down, and you can measure, for example, by Kerr microscopy. In the orbital Hall effect, it's not necessary to break time reversal symmetry, it's not necessary to have a spin-orbit coupling, but your material must have a multi-orbital texture with a non-trivial interorbital hybridization. I will talk more about this. And then, again, you apply electric field. This generates a transversal current, orbital current that accumulates. You can see as electrons in one side of your sample are turning clockwise around the nucleus, and the electrons in the other side of your sample are turning counterclockwise around the nucleus. So this is the phenomenology of the orbital Hall effect. So how it occurs? This was introduced in a very important paper in the area by a Korean group. They consider a multi-orbital model made of S and P orbitals. This model respects time reversal symmetry. The model is a central symmetric. It respects spatial inversion symmetry, the Hamiltonian of this model. Under these conditions, the block states do not have an equilibrium orbital angular momentum. You cannot, the orbital texture to each k point in our Brillouin zone is enforced to be zero by symmetry if you have time reversal and spatial inversion at equilibrium. But the author shows that if you apply electric field, appears a non-equilibrium orbital texture associated to correction in perturbation theory of your states through the Brillouin zone. And this non-equilibrium orbital texture is distributed around the Brillouin zone in such a way that generates a transversal current polarized in orbital angular momentum. This is illustrated in this figure here. Is a similar mechanism that occurs to spin. But the authors also argue that orbital Hall effect is more fundamental than spin Hall effect. They show in the blue curve the orbital Hall effect as a function of spin-orbit coupling, and orange curve is the spin-Hall effect as a function of spin-orbit coupling that goes to zero at zero spin-orbit coupling. And when you turn on the spin-orbit coupling, part of the orbital Hall conductivity is transferred to the spin sector, giving origin to the spin-Hall effect. So the orbital Hall effect precedes the spin-Hall effect in some sense, at least in the view of this paper. So this is how the effect occurs. And now this was an overview of orbitronics. Let's talk about our work on orbitronics in 2D materials. Here is how we compute the orbital Hall conductivity. The orbital Hall conductivity can be written as an integral through the Brillouin zone of an orbital Berry curvature. And to calculate this orbital Berry curvature, you have to give two ingredients. The first one is the details of electronic band structure, or eigenvalues and eigenvectors of your Hamiltonian in reciprocal space. You can calculate it using DFT calculations, tidy-mild model, low energy model, as I do. And the second ingredient is less trivial. You must know how to write the orbital angular momentum operator to your solid. It's not trivial. If you do tight binding model or if you do low energy models, it's easy because you are in the tight bind basis. If you do the FT calculations, it's more tricky, but it's possible. There are some technical sophistications here. I'm using intratronic approximation that view the orbital angular momentum of your solid as the orbital angular momentum of individual atoms. In real systems, this is not the truth. The electron can translate to many atoms, but let's forget about these technicalities. And with these two informations, the electronic structure and the orbital angular momentum operator, you use this equation to calculate orbital Hall conductivity is the proportionally constant between the applied electric field and the transversal current you generate. Okay, so to keep going, I will come back to the spin sector and talk about the paradigm of quantum spin Hall insulators proposed by two guys, the Kane and Mel. In the quantum spin Hall insulator, you have a bulk band gap. You have the spectrum. The spectrum of your bulk system is gapped. You have a gap in electronic spectra. If you put the Fermi energy inside this gap and use analogous calculations to the previous one, you can calculate the spin Hall conductivity. And in the Kane-Mel model, disregarding the Hashbach coupling for simplicity, if you do this, you calculate the spin Hall conductivity, you will find this famous plateau, the spin Hall conductivity plateau. The spin Hall conductivity plateau without Hashbach coupling is quantized. the spin-Hall conductivity is proportional to a topological invariant we call spin chair number. The spin chair number is a topological invariant in the sense that you can perform smooth modifications in your Hamiltonian, and that the topological invariant remains quantized. If you cut your system in a nanorainbow geometry, will appear these edge states crossing the book band gap region. These edge states are responsible for the conduction of this spin-Hall conductivity. So this is the paradigm of quantum spin-Hall insulator. You have a plateau in the spin-Hall conductivity. You have a topological invariant associated to this conductivity. You must have edge states when you cut your system in a nanorainbow geometry. Now, at some point, we started to look for this famous material, the TMD in two-age structural phase. Everyone knows here the lattice structure of the TMD is shown in that picture. The TMD is an insulator. It have in the book electronic spectrum, it have a huge band gap. If you project near the top of conduction band, in the bottom of conduction band and the top of valence band, the orbital characters of Bloch states are written there, DZ2 at the conduction band, and that complex combination in the valence band is easy in a tight bind base to attribute an orbital angular momentum operator to this Hilbert space. You can calculate the energy levels and wave functions also using DFT calculations, and put on the formula I showed previously and calculate the orbital Hall conductivity and the spin Hall conductivity with analogous expressions. So if you do so, you will obtain this result here. The red curve is the spin Hall conductivity, and look for the shaded region that is for Fermi energy inside the book insulating band gap. The spin Hall conductivity for monolayer TMD is 0, as Philippe said yesterday. Is the monolayer TMD is not a quantum spin Hall insulator, is trivial from the point of view of electronic spin, but we found an orbital Hall conductivity. The orbital Hall conductivity when Fermi energy is inside the energy band gap have a plateau, similar to the plateau in the Kahn-Meli model, but here for electronic orbital angular momentum sector. Similar, not equal, is similar. Okay, so this resembles us the physics of quantum spin Hall insulators, but we have to define 2 more ingredients. And we do this in 2 papers. We was able to define orbital chair number similar to the spin chair number. If you do your calculations in the low energy regime, approximating your monolayer TMD by a Dirac Hamiltonian and do the things by paper and pen, you will find that orbital Hall conductivity is proportional to the orbital chair number, very similar to the spin Hall conductivity in the Kahn-Meli model is proportional to the spin chair number. This orbital chair number is a topological invariant in the same sense that you modify some parameters in your Hamiltonian, the topological invariant remains the same. If you cut your TMD in a zigzag nanorainbow, you will have these edge states crossing the book band gap energy region. So the picture is that monolayer TMDs have a physics similar to the quantum spin Hall insulator in the Kahn-Meli model. There are differences if you continue your analysis. I'm not saying that is the same thing, but at least some ingredients are similar. But now happens in the electronic orbital angular momentum sector. Later, we keep working with Fazio and Gabriel in another paper exploring the connection between orbital Hall effects and high-order topology, but I will not talk very much about this here, just because it's a more complicated issue. Later, this is paper from other groups that keep evolving the idea of orbital Char number. They show that orbital Char number are susceptible to topological phase transitions as spin Char number. So you here a topological phase transition for an orbital Hall insulator with non-trivial orbital Char number to a trivial insulator with trivial orbital Char number. There is another paper exploring topological phase transitions between Char numbers with high order, and some people now are using this topological invariant associated to electronic orbital angular momentum. So from orbitonics, I think this is what I want to say. I make part of a group in Rio de Janeiro that intensively work this topic of orbitronics. We are, the group are growing. It started with a very small group 5 years ago, and we are now looking for other direction, the treatment of disorder, real space calculations of orbital Hall conductivity and orbitronics effects. The third topic is pushed by is particularly pushed by myself, is how to go beyond this view of intraatomic approximation of electrons orbiting the nucleus and start to consider the orbits involving many nucleus. Is a more theoretical concept, and I pushing much more the topic 3 than the other 2 topics. We write a review on orbitronics of 2D materials. We resubmitted this review a few weeks ago. We waiting for the response. We are very optimists because the first round was good, and we are waiting for the second round. But the preliminary version is on archive if you have interest. This is the core of the group. Bechara, Tatiana, Márcio Costa, Adalberto knows very well, Luiz Canônico, me. So just 3 minutes, because I started a position at youth a few months ago, and I start to do other things. The focus of the talk will be orbitronics. The focus of my research in the last years will keep orbitronics, but I try to do other things. I'm showing here just few papers that's in other areas that I have published. I have some interest in nanophotonics of 2D materials since my master. I do some things parallel in nanophotonics. So here we study how to control this nanophotonic effect of anisotropic resonance energy transfer between emitters near a phosphorescence sheet under strain. Recently, I start to study this new area of local topology, and we wrote a paper with a collaborator from that's now in the United States of local spin Char marker in generalizations of Kane-Meli-Hashba model, and how you describe your topology not in the Brillouin zone but in the real space. So this is with the collaborator Sebastião, and recently I also do this work in quantum fractals. Maybe is an emerging field, quantum fractals. There is a famous name, Brazilian name, Cristiane Moraes Smith, that is working intensively quantum fractals. So we use this local spin Char number to study the real space topology, And I done this with Andrea Latiger from NUF. Lucas is a PhD student. And I'm now professor at UF. This is the view of the building of Federal Fluminense University. We have this nice view. It's a beautiful beach. You can swim a little bit. It's just the Guanabara Bay. But it's a very nice place to work. It's a very pleasant university, so you can visit us if you have some interest. And thank you very much for your attention.
Thanks a lot, Tariq. Talk about these odd physical effects. Very good. Questions?
Thank you, Tariq, for the presentation. So let's warm up. You mentioned many analogies between spin Hall and orbital Hall. Can you comment a little bit on where they do not behave equally, especially regarding your point number 1, where locally you can break symmetries, so like disorder effects and so on. This is like...
I will focus on the first part of your question. A much more evident point in which they are very different. I'm showing here the X spectra of nanorainbow cut in the zigzag geometry of the TMD. And you have these edge states crossing the book band gap. If you do the same thing in the Kane-Meli insulator, you will find edge states. But in the Kane-Meli, you can also cut your system in armature direction. And you will have also the spin polarized brands crossing the book band gap. If you cut your TMD in armature direction, you will have no edge states cross the book band energy gap. This is related with our work suggesting that, we calculated it. The TMD is actually a high order topological insulator. This view is not completely lost because you can associate high-order topological insulators with chair number if you use the appropriate symmetry to define your chair number. And this is the point that I was failed because I spend a lot of time trying to find this symmetry, and I never do that. Sometimes I go back, try to review my calculations, but this not happens in the quantum in the quantum spin Hall insulator model. So what's lost is this to make the connection, the full picture of this topological phase is this definition of a chair number to a crystal symmetry. It is nothing to do with quantum spin Hall insulator. It's a high order topological insulator, but I do not yet manage to do that. If I do so, I will tell you, and you try to do another paper. But this is the point that they break. Is the quantum spin Hall insulator have nothing to do with high order symmetry or with high order topology, but here the TMDs have a relation with high order topology. It's more complicated.
Okay, thank you for the nice talk. My question is, would you say a few words about the experimental measure of orbital? That's a big discussion that you're having.
So
and recently, the group from University of Pernambuco, is a PRL recently.
The Azevedo group. So there is two things. Most of experimental, both theoretical and experimental efforts on orbitronic are dominated by three-dimensional material community. Okay, the two-dimensional material community that starts to work with this. Still incipient, but is growing. I will show an experimental paper that I was involved later, but we have this point. So in 2D materials, the results, the experimental results, is still very incipient. In three-dimensional materials, there are many results, but as a very new field, there are some experimentalist issues to make the differentiation between spin signature and the orbital signature, and people start to learn how to do this. There are some results that are clearly orbital, and there are others that spin may have generate some confusion. In 2 dimensionals, there is really few papers with experimental comparing experimental and theoretical results. But this is one paper. I make part of this paper. The experimentalists built this device here of twisted bilayer graphene. They open a small band gap because they use a very small a twisting angle very far from that magic angles. It's just to open the gap. They built that device that's able to detect non-local resistance measurement resolved in the valleys. So if you connect one terminal, you are seeing at the valley K, and in the other terminal, you are seeing at valley K prime. Here in the top, I'm showing the experimental results, and in the bottom, I'm showing the calculations of orbital Hall effects. So this is an experiment. They are clearly correlated. You have some correlation between non-local signal and the orbital Hall conductivity. But again, for 2D materials, there are more 2, 3, 4 papers of such type. Okay.
Well, a very nice presentation, and congrats for your new position.
Thank you.
When we look at the conductivity, we realize that we use the word quantum, but the conductivity seems that it's not quantized. It's 2 point something, right?
Yeah.
It's 3 point something. And this is the first question. Can you comment about this, please?
Yeah. The same thing occurs in the quantum spin Hall insulator if you turn on hashback coupling. If you turn on hashback coupling and calculate the spin Hall conductivity, the plateau will not be quantized. They grow a little bit. So, but you still can define a chair number in the presence of hashback coupling using a different procedure. Introduced is more technical, but you can still define a chair number, but the conductivity is no more proportional to the chair number. You lost this proportionality. And to define this orbital chair number, I do this procedure that involves a projection in valence band subspace, a rotating.
Yes, and the second very quick question is, when you introduce the Rashba effect, and then the angular momentum is no longer a good quantum number.
Yeah.
Right?
Is the reason.
So, and then my question is, what is the meaning actually of the orbital current? I mean, if it's not a good quantum number, how you can measure that, and what is exactly the meaning?
I understand your question. How to because when you introduce the Hashba effect, you lost the continuity equations of the spin operator. Is more technical, and you must to introduce a torque term in your continuity operation, but this torque term is a Fermi surface term as long as all the torque terms I see, and at least for insulator, this torque term should be 0. in the orbital Hall conductivity, similar things should occur. But this is related to the definition of spin current. I don't know if you see this debate. Some people says that you must define your spin current in a different way. Some people say that you must to add the Stark term. Some people say that you must to include vertex correction, and without vertex correction in your calculations, the things make no sense. But this is a debate. I never see a conclusion about that. I just say that in the insulating phase, we keep safe because the vertex correction should be zero. The torque term is a Fermi surface phenomenon, should be zero. So this is an issue for metallic systems. Okay?
Interest of time, we should go for the coffee break and thank both speakers of the first part of the morning. And it starts again at 10:50, 50, yeah? Oh no, 10:40? Well, we'll call you back. We'll call you back. No.
10:20.
No.
10:40, 10:40, 10:40. Me perdi.
The next session will be starting soon, so please come back to the auditorium. The next session will be starting soon, so please come back to the auditorium. The next session will be starting soon, so please come back to the auditorium.
O pessoal escreve assim, ABC Federal. Eu deixava a Universidade Federal da ABC.
Você já viu alguém traduzir École Polytechnique para Polytechnical School?
So good morning, everyone. So I'm going to be the chair for this last session for this meeting. And we are going to actually have two talks. Mariana said early 3, but it's only 2. So Carlos is going to be the first one, and then we're going to have the Maurice's talk. So Carlos, he's also part of the big family. So he was FASU students for the master and the PhD. Then he did a postdoc with Gustavo Dalpiana and also with Alex Unger in the US. And now he's a professor at the Universidade Federal do ABC. We are joking that in English becomes Federal University of ABC. And ABC is not the primary school. It's just because it's the metropolitan area of São Paulo. A, B, and C is the name of the cities over there. So Carlo is going to talk about unified magnetoelectric mechanism for spin splitting in magnets. So Carlos, please.
Thanks, Luana. And yes, I started this year with a position in the Universidade Federal do ABC. It's curious the naming, ABC Federal University. Well, the main idea of this talk is try to present a proposal to explain spin splitting in materials. This is the main idea. So trying to maybe put the question in a simple way, when we have the band structure, essentially we have 2 degrees of freedom here in which we can separate the spins. Essentially, we can see here that we have the momentum and the energy. And the main idea is that you can have a discrimination of spins in both degrees of freedoms. For instance, in energy, you will have this kind of separation between bands with opposite spin. And for sure, you can have something similar in the momentum. So now you have this spin splitting in the momentum space. That's the idea. Well, it turns out that this is well known, and usually the spin splitting and the energy degree of freedom is called as Zeeman effect. This is what we know as Zeeman effect. And you can understand this using a very simple term, that is the matrix Pauli times the magnetization, right? And it occurs when you have a net magnetization different from 0. Well, when we have a non-centrosymmetric material now, you have a spin splitting in the momentum space. Now you can see that the bands are actually separated in the momentum space, and you also have that each of these bands have a opposite spin. And the mechanism behind this behavior is a spin-orbit coupling. And usually what we have is the matrix Pauli times the wave vector here. And this is usually known as Rashba effect. We also have in this group the Dresser-Haus effect and other kind of effects that are related with the breaking of inversion symmetry here. Well, it turns out that in last 3 years, people realize that when you have 0 magnetization, this means that it's not related with the Zeeman effect. And when you have acentrosymmetric, which is essentially means that it's not related with the spin-orbit coupling, you can also have a spin splitting. That's the point. And in some way, this contradicts, at least I would say that the last 100 years of understanding of magnetic materials, and also the understanding of spin splitting. This is usually called as altermagnetism, okay? And the main idea is that you have an antiferromagnetic system. You have 2 antiparallel magnetic moments, right? And in some way, then they cancel the magnetization, and they are also centrosymmetric, can be centrosymmetric. And the big question here is, well, what is the mechanism behind this behavior? That's the idea, okay? And I'm going now to share with you my possible explanation to this phenomenon. That's the idea. So we are going first to try to understand the Zeeman effect, the Rashba effect, and then I'm going to explain you how I maybe put some equations to try to understand this spin splitting in the altermagnetic materials. And as everyone, I will start from the beginning. The main idea is that in general, in a material, you have a possible, let's say, source of interaction or field that is electric or magnetic. Usually we understand them in terms of the electric dipole and magnetic dipole. And you can put this in a specific chemical environment. So you can accommodate this dipole that is magnetic or electric inside a specific, let's say, distribution of atoms around a specific center, okay? So you have something like this, and it's very simple, but it gives you two things. First, the local symmetry of this, let's say, chemical environment, and also the source of the field that, again, can be electric or magnetic. Well, the idea is that you can combine these kind of sites and motif to have a crystal. And this is how we can actually understand materials. And the idea, just to give you an example, is that, for instance, if you have a centrosymmetric system, you can actually move atoms here, okay? And when you move this atom, you will create an electric dipole because you don't have a cancellation of the, let's say, electric dipoles formed by the bonding, atomic bonding here. Well, in the same way, you can actually put a magnetic atom in the center of the interaction, so you will generate an electric dipole there. This is how we usually understand this. Of course, this is a minimalist view of the phenomena, right? And the nice thing is that when you put these things together in a crystal, then you also can have an additional degree of freedom that is related with the symmetry of the wave vector. So each wave vector here can actually have a different behavior. That's the main idea. Well, and additionally, of course, you can have all possible combination between these things. For instance, you can have a material that is non-centrosymmetric and non-polar, so the opposite dipole cancel each other. You can also have, for instance, an anti-ferromagnetic system that is two different anti-parallel magnetic moments that cancel each other, and then you will have, in principle, many other combinations of these kind of local motifs or local fields, plus the symmetry that explains the interaction in a given chemical space or given chemical environment. Well, so now we have to add the spin in this discussion. The idea is that you put the spin in the orbitals, and then you have the band structure. The band structure looks like something that we can put in a minimal view as a parabola, right? Just the quasi-free electron. And we have that each of these bands here have two electrons, let's say, with opposite spin. And the idea is that the spin we see here in the band structure is not actually the electron spin, it's something different. The spin we see in the band structure is something that you get when you, in principle, include all of these local dipoles, electric and magnetic, in the Hamiltonian. And if you solve this in a good way, using all the approximations you want to have something similar to what to the experimental view of the energy dispersion, you can actually compute the expected value of the spin operator. This is essentially the Pauli matrices, and you use the wave function to compute this expected value. So essentially what you see in the band structure is this expected value, right? It's not exactly the electron spin electron, but it's a collective behavior that gives you the band structure with a specific spin direction for each band index and each way k vector, right? And as already you saw in the previous presentation, the main idea is that you can use this to try to make devices. So for instance, you have a ferromagnetic system here and other ferromagnetic system here, and they have opposite magnetization. You can actually try to detect the electrons, or the current, sorry, with a specific spin, and control the electron current here with a specific spin to have, for instance, 0 or 1, as we do in a transistor. Well, very good. So now I'm going to explain that this electric dipole and electric magnetic dipole are not the only source of fields that we have in materials. First, to make this clearer, I will show you that when you have the electric potential, in general, you actually have charge, right? The dipole and the quadrupole, and you can have additional contributions, for instance, the octupole source of the electric potential. And the idea, in a simple way, is that the charge gives you, for instance, a completely spherical symmetry. This means that the inversion symmetry here is preserved. Here, you will have that the inversion symmetry is broken because, for sure, you have two different sources of charge, for instance, in the dipole configuration. And when you look to the quadrupole source of this electric potential, you again have the preservation of the inversion symmetry. This means essentially that if you have this center here, you can go to one atom here, and this goes to this place, so you don't break the inversion symmetry. Okay, very good. So, and then people say that you have actually electric multipoles. Okay, charge, dipole, quadrupole, octupole, and so on. Well, and as you already saw there, when you put here this -1 here, means that you are talking about the spatial inversion symmetry. For instance, 0 will stand for the L equal to 0, the charge. L equal to 1 means you break the inversion symmetry. This means the dipole, and so on. Very good. So now, when you look to the magnetic contributions, at least for instance, to the dipole, magnetic dipole, we can make a nice differentiation here, because this other term here stands for the time reversal symmetry. And electric dipole or electric sources don't break the inversions, the time reversal symmetry. However, magnetic dipoles, as we already saw in the last presentation, can actually break the time inversion symmetry. And then maybe I think that 50 years ago, some guys in Russia say, well, let's complete this view, okay? What is the idea? If you have here -1, 1, and you have here -1, -1, maybe we can actually complete this view, putting here -1, 1, and here, of course, you have both as -1. And this is usually known as toroidal magnetic multipoles. This means you have a magnetic configuration, right, with specific multipoles that form a kind of a toroidal configuration. And you have something equivalent that is the electric toroidal multipoles. So you have all of these contributions in nature. And what is very special of this is the following. If you put all of these multipoles, in principle, you will have the complete Hamiltonian describing any material. That's the idea. And or at least from the point of view of the breaking of time reversal symmetry and spatial inversion symmetry. Very good. Now, we can actually analyze what is happening with these contributions. For instance, when we look to the electric monopole, we have only charge. So in this simple view, we have just the parabolic band structure from the electron, right? This is the kinetic energy that if you make a cut here, you will see that the Fermi energy surface looks like a concentric circle. And if you put the electric dipole in this description, you will see that, as already mentioned, you have this breaking in of the degeneracy of spins in the momentum space. And this is usually known as, I mentioned, Rashba effect. And you will see that the spins here are actually tangential to the Fermi energy surface. Okay? Very good. So actually, is something very, very curious, because maybe already 70 years ago, Rashba proposed that if you have a material that is not centrosymmetric, you will have this very simple Hamiltonian giving you this spin discrimination. And at least maybe 10 years ago, people realized that you can obtain a similar behavior by putting here an intrinsic electric dipole. So now this is known as intrinsic Rashba effect. And Rashba passed away this year. I have the honor to meet him. And well, I think that we have a very nice contribution from him in physics. For instance, that if you change the direction of the electric dipole, you actually would change the direction of the spins. And this is very, very good because we know this as ferroelectric material. The idea is that you apply an electric field, you move the atom that is in the center, and then you change the direction of the electric dipole. Very good. So in the last 10 years, I would say, in the group of Facio and Daupian, I invested a lot of time trying to understand this physics. I'm going to show you a couple of examples, and then I'm going to move to the source of this altermagnetism that I'm going to explain in this presentation. Very good. Something that is additionally very, very nice is that if you take the symmetry of the problem, okay, for instance, the character table, you can actually have the terms that are in the Hamiltonian for sure a toy model. For instance, for the monopole, you will have these representations and these kind of parabolic bands. If you go to the dipole, for instance, which is not centrosymmetric, you will have something similar to the Rashba effect. And of course, if you go to the quadrupole, for instance, you have this kind of K square contributions to the Hamiltonian. Very, very good. So the curious thing is that none of these contributions explains, of course, the magnetism, because we are focusing here first on the electric behavior. But well, you can do, for instance, calculations. We do at least 2,000 systems to analyze what make a material to have a large discrimination of spins. You can filter then, and we propose a mechanism that we call the Rashba scale, that explains that if you have band anti-crossing in the bands, you have very large spin splitting, and you can see that this behavior explains what is happening in many of these materials that were experimentally realized, and you can find in the Materials Project repository. And we also invest time in understanding, for instance, how to design materials that allows you to reverse the spin direction when you change the electric dipole direction. And we also, for instance, propose a possible device using this kind of band inversion and non-trivial topology together with the Rashba effect to control how the electrons goes from the source to the detector. And I would say that this all together and the physics behind the electric dipole is very well known now. However, of course, when we go to the magnetic multipoles, this seems very, very simple, and no more discussions we observe after the seminal paper of Zeeman that was at least, I would say that now 140 years ago maybe. And Zeeman found the following. If you have this system and you apply a magnetic field, or you have an intrinsic magnetic dipole, you will also promote the discrimination of the band structure in terms of the spin direction. Something that is very nice here is that the spin is aligned with the magnetic moment here. So you again have this K squared contribution and the magnetic contribution. And well, we know now that we can actually obtain different kind of behaviors, thinking on how you accommodate the magnetic dipoles in the crystal. For instance, we did a nice work with Gustavo, trying to understand with machine learning and ZISO actually how you discriminate ferromagnetic from anti-ferromagnetic two-dimensional materials. Is a very nice work in which we find good descriptors, for instance, to classify these two groups of systems here. That in some way we realize that the spin-orbit coupling is very important for this classification. Very good. So now let's go to the magnetic toroidal and electric toroidal. And it turns out that, as I already mentioned, that besides these two very well-known dipoles, we can actually have this electric toroidal and magnetic toroidal. And it's not very well known what is the meaning of this dipoles or multipoles contribution. But what is very clear is that in all of these situations, when you have two concentric cycles, okay, you will have discrimination of the spins. For instance, look, electric dipole, you will have magnetic dipole. You will also have the possibility to have discrimination between spins with the electric toroidal monopole, and also here, look to this magnetic toroidal dipole, okay? Something that is very nice is that when you look to this Venn structure here in 3D, you will see this energy dispersion. Essentially, you have, again, a spin splitting, and now the spin is, again, aligned with the magnetic moments that you put it together to construct this kind of magnetic toroidal. Well, and it turns out that when this appears, maybe 4 years ago, people call this as a new class of magnetic materials. This means essentially that when you have these ferromagnetic systems, this means this very only one magnetic moment in the Brillouin zone to giving you the Zeeman effect. Of course, when we put two of these guys, you will not have any spin splitting, but these guys in this paper that was published in the PRX, they try in some way to sail a new term, a new idea that they call altermagnetism. The idea is the following. Now you will have something that is very similar to anti-ferromagnetic configuration, and then you have a up magnetic moment, down magnetic moment, but you have a spin splitting. So the question here is, again, if you have zero magnetization, then how you explain the existence of the spin splitting? And the idea that they put in the paper was the following. When the magnetic motif, I mean, not only the magnetic moment, but also the chemical space around the magnetic moment is rotated one to respect to the other, then you will have this kind of spin splitting. That's the idea they put in the paper. Of course, all of this can be explained by symmetries. You can put this group theory and show that actually the spin splitting is allowed and so on. However, the mechanism, I mean the physics, is not so clear. Okay, and you can actually saw this in real materials. For instance, this is the case of manganese fluorine, right? And as you maybe can see here, we have a spin splitting in some specific directions. There is no spin splitting in the whole band structures. And again, you will have these two motifs connected by rotations. That's the idea. And of course, this was actually measured this last year and actually these years. You can find amazing papers showing ARPES demonstrating the existence of this spin splitting. And also you can see that there are some challenges to measure this spin splitting. For instance, the magnetic order, the temperature, and for sure the quantum anomalous Hall effect, because when you have a spin splitting, and in principle you can think about magnons and different behavior. One of these is the existence of quantum anomalous Hall effect in these systems. Well, now I'm going to start to explain what I did to explain these kind of systems. Very good. So this started in the following way. With Alex and Lyndon, we realized that the whole physics can be understood in terms of the connectivity between motifs. Let's say if we have a magnetic moment up and it's the same that a magnetic moment down, then we don't have a spin splitting. But if these local motifs are different, this means that you cannot connect them, for instance, by translation, as in a conventional antiferromagnetic, or you cannot connect them by inversion symmetry, as in a conventional antiferromagnetic, you will have this spin splitting. In other ways, you need to break both the UT, that is the translation symmetry and the spin inversion, and other symmetry that is the product between inversion symmetry and time reversal symmetry. When you do that, and then you will have a spin splitting even without a spin orbit coupling. That is the important thing here. You don't have magnetization and you don't need the spin orbit coupling to have a spin splitting. This can occur actually in both anti-ferromagnetic system and ferromagnetic system. This is not just a behavior related with anti-ferromagnetic materials. And actually we propose in this paper that you can put together different layers and then you can connect and play with the symmetries you preserve and you break to construct a possible spin splittings. Something nice is that there is a way in which you accommodate all of these layers to ensure that you don't have a spin splitting in any of these systems. The nice thing about this is that when you break the symmetry, I mean, they are no longer equal. For instance, applying an electric field, you will have the spin splitting again. So the idea is that you apply the electric field, and then you can control the existence or absence of the spin splitting. And of course, you will see a big table explaining how you can construct and put together of these layers to preserve now the spin splitting. Very good. Let's now talk about the mechanism, I mean the physics behind. To do that, the first thing is that in principle, these two Hamiltonians are the same. I mean, all that we compute, for instance, from the FT, and all that you compute using the multipoles expressions should give you the same results. Here you will see that you have external multipoles, internal multipoles, and the Hamiltonian related with all of these possible contributions. Here, there are some source of these kind of multipoles. For instance, you can check here that the magnetic multipole is, of course, induced by the magnetic field. And the electric multipole is induced by an electric field. Very good. So what I did was the following. I started with the Dirac equation, okay? And then I wrote the Dirac equation in terms of both these large and small contributions. And here it is important to note that this pi here is no longer the momentum, but is the covariant momentum operator. The idea is that you have here not only the momentum, but also the contribution of the magnetic vector potential. Good. So if you try to do some math here, you will realize that you can write this equation in terms of only one of these contributions. For instance, the large spinor component of the wave function. And then you have something like this. This is a solution from textbooks, okay? What we usually do, and actually do that in my master project, because I have the task of introduce the spin orbit coupling in the Siesta code at that time. And I work hard and just to try to understand how to this Taylor expansion here. You can see that you make this Taylor expansion and you have many terms here. And you can maybe take these two first to try to make an approximation. For instance, for the first one, the eta 0, you have a constant. And for the other one, eta 1, you have this term here that depends on the electric potential. Very good. So it's clear that if we take the first one, I mean the constant term, you just introduce the constant in that term. So you will have this product here, okay, with a constant in the middle. And then this constant gives you essentially this equation. And you can solve this equation in a very simple way, just using the basic relations of Pauli matrices. And when you do that, you will obtain what is called the Pauli equation. And this is known at least 100 years ago. And it's very, very nice because the Zeeman term, this means the spin splitting induced by the magnetic dipole appears in a natural way, just on a zero-order relativistic contribution, right? And it's essentially this one. You can relate these terms by simple inspection. Now let's take a look to the second term here, that is the first order relativistic corrections. Then you need to introduce now this term here inside these parentheses. So you will have this equation here, right? the nice thing when you do that is that you realize that the electric potential not necessarily commute with the momentum. So even though if you introduce this expression here for the electric potential, you need to take into account that this commutation here is not equal to 0. Very good. So what we do, just take this commutation relation and put there, and you realize that 2 terms appears here. This first one that depends on the gradient of the potential, and other one that depends linearly with respect to the electric potential. And here's come the nice physics. When you put these 2 terms and you operate with the other product, I mean, you have all of this with the second one, you will see that you have 2 things first. The first one is the spin-orbit coupling that is very well known, and the Darwin term. So this is a very well-known physics, and actually we know many physics that is behind this spin-orbit coupling. For instance, the spin Hall effect and other things. But when you look to this term, you will see that this product here, okay, will again give you something similar to the Pauli equation. I mean, something that depends on the square of the momentum pi. I'm just taking these 2 guys here, okay? And you can notice that when you apply the relation between the Pauli matrices, you will get this behavior. And this means essentially that besides the correlation to the kinetic energy, the spin-orbit coupling, and the Darwin term, we have an additional term here that I called magnetoelectric relativistic correction. And it's very curious, look, because when you look to the Sakurai, maybe the students will realize that, and it's page maybe 407 something, the Sakurai book does the following thing. Just remove the pi here, the canonical momentum, and replace by putting P. This is just the momentum. And when you do that, you just lost this term, okay? And it's curious because when you look to the old textbooks, all of them treat in a separate way the relativistic corrections coming from the electric field and those coming from the magnetic sources. So for some reason, they don't look to this term that should be appears here. And of course, there are these Bright equation that is a correction to the magnetic field, and it's something similar to this. And the nice thing, that I'm going to try to demonstrate to you the following thing, that now, if you put this in the Hamiltonian, all the physics about the altermagnetism appears in a very clear way. You will see that is now in some way obvious that the spin splitting should be there. So then we just try to understand this. The idea is that you put 2 magnetic sides with opposite magnetic moment, right, with different electric potential, and we do that. You have, for instance, this rest of these two terms, the potential from the first side and the potential from the second side, and this with the product of something that looks like the Zeeman term. Very good. So this means that in some way the difference between the potentials cooperate to give you a new results. And what is important, again, is that they should be different. If they are equal, maybe the cooperation should be not so representative for this kind of terms. So now you can see that this essentially explains a very simple physics, why the motifs should be actually different. And that is something that is even amazing, is that now we have a third term that completes this description of the spin splitting in materials. We have something that gives you the separation in the energy, something that is known, of course, as spin orbit coupling, that gives you the separation in the momentum space, and something that combines the two behaviors, electric and magnetic, and give you both separation in energy and separation also in the momentum space. And this magnetoelectric correction can actually be understood from different sources. For instance, we can focus on the dipole. and the charge. So we need, essentially, we can have something that is similar to two magnetic sites with different charge. This was actually, we can also have something that comes from the dipole. I mean, besides the magnetic moment, we can have the electric dipole there, and something that is related by rotations and comes from the quadrupole electric source. Very good. So it's nice to see that when we look to the charge contribution, we have something that depends on the magnetic moment, but it doesn't depend on K. This means we have a spin splitting at gamma, okay? Even in an anti-ferromagnetic system. And it's nice to see that last year my friend Linding Yuan showed actually that you can have this spin splitting here at gamma, and this spin splitting is essentially obtained by doping the lattice and obtaining this different on charge on these different magnetic sites. And for instance, we can now focus very quick on the quadrupole. And the idea is that you take the quadrupole matrix here and you transform by using a symmetry, of course, a crystal symmetry, from one motif to another motif. When these two guys are different, for instance, by sign, then they cooperate together to give you a non-zero spin splitting. When they are the same, then the term just cancel, okay? So you can understand this using just the symmetry to transform the matrix quadrupole here, okay? So, and we realize something that is even nicer, that is that when this is very symmetric, the magnetic motifs, I mean, you can understand these as atoms here, okay? And there is no charged dipole or quadrupole. Even if you have an anti-ferromagnetic system like this, there is no, of course, spin splitting, they just cancel. When you promote an actual axis, for instance, by making something like a strain, or just picking up a side that is have this configuration, then you will have a kind of quadrupole matrices that is diagonal. So just to summarize, you have here 0 quadrupole, and then these have a linear quadrupole matrices. And the idea is the following. Well, if this is correct, and we can, for instance, take all possible matrices that we can have in different sites, and all possible crystal symmetries connecting them. And this is what we actually did. We take all possible canonical form of the matrices. Here is the diagonal one. This is another kind of diagonal. This is, for instance, when you have at least one term in the off diagonal, and when you have all terms that are non-zero. And if you do that using materials informatics, for instance, you will see that there are specific site symmetries that give you this quadrupole configuration. For instance, of course, if you don't have any symmetry constraint, you have that all matrix elements are different from 0. If you have something that is almost symmetrically, spherical symmetric, you will have that all of them are 0, and then you have here a combination, of course, when the site is centrosymmetric, non-centrosymmetric, non-polar, and non-centrosymmetric polar. These are the 32 site symmetries we can consider, okay? And to give you these matrices. And the nice thing now is that you can actually evaluate which symmetry operations from the crystal, okay, can give you a spin splitting 0 or different from 0. The idea is the following. You just take the symmetry operation here and you evaluate if there is commutation or not with the matrix. If you do that, you will realize, for instance, that in all of these cases, the inversion symmetry gives you a commutation relation equal to 0. This means that the dipole matrices doesn't change, okay? If you take the identity, of course, the matrices also doesn't change. And of course, when you make compare the two matrices, it gives you 0, okay? But we can also realize, okay, that there are some symmetries with the specific relations with the axial axis, for instance, or with respect to the planes that will give you a change in the matrix. When you have, un minuto, okay. When you have this change in the matrix, then you will have a spin splitting, okay? And we do that, okay? We do that and we check all possible kind of k-dependence with respect to the wave vector, okay? And I have only 1 minute, so I'm going to only to change that. You can just apply this term to check the dependence for any material you want, and you realize that actually it explains in a very good way all the degenerescences you will observe in the band structure and all of the spin splitting in all directions in the band structure, which is very nice because this is just an example, but you can extrapolate to other cases. Well, some take-home messages. First one is that we obtain this electromagnetic correction to explain the spin splitting in anti-ferromagnetic systems. It should also exist in ferromagnetic materials. The second thing is that this correction explains the connection between magnetic motifs. And of course, that altermagnets, and something that is very curious is that when you look to the papers published in the last 4 years, people may have a confusion, I would say, that because you don't need a spin orbit coupling, most of these papers say this is non-relativistic effect, okay? But the exclusion of the spin orbit coupling, it doesn't mean that the spin splitting is relativistic or not. So we show that the altermagnetic spin splitting is actually a relativistic effect, that there are different regimes for the altermagnets. This means charged, dipole, quadrupole, and octupole, that there are other symmetries connecting magnetic motifs like mirror symmetries, not only rotations, and of course that altermagnetics can be seen as a multiferroic materials. So finally, I would like to thank first to Beto and Gustavo. I have worked with them last 10 years, and this year, as I mentioned, I'm back here in Brazil with FABC. I'm very happy about that, and it's actually kind of honor to me be part of the big group with, as Gabriel mentioned, a lot of brothers and sisters and cousins here. Also, thanks to Lindy and Alex and Alexander that are now in different places. Something that are very important, James and Pedro Utreto, that in the UFABC allows to have this very big and nice central computing center. This is amazing work, and of course, Mariana, Facio, and again James for organizing this nice event, and all my collaborators, and mainly to my students, Raynel and Valeria. They started now the PhD project here with me, and we are doing very nice and amazing things. Thanks to you, and this is the preprint. You can check in archive, and of course, if you have questions and you want to discuss with me later about this, you can write to me in this email. Thank you.
Thank you, Carlos, for your talk. We have time for a few questions. Pedro, over there.
Hi, Carlos. Thank you very much for your talk. It was an amazing talk. My question is it possible we can observe the transition magnetic phase when we dope altermagnetic materials? I mean, when beyond the dipole and quadrupole contributions?
Yeah, thanks, Pedro, for your words and your nice question. And of course, I mean, the short answer is yes. I mean, all possible electric multipoles you can have in this behavior. Usually, the idea is that as you increase the order of the multipole, you will have a smaller correction. So octupoles and decapoles and these things maybe contribute less than the dipole and the quadrupole. But look, this is not a final answer. I mean, in some cases, and people realized that last year, decapoles, electric decapoles and magnetic decapoles can contribute very huge. But for some reason, they didn't make the link with the Dirac equation and what is the mechanism behind this behavior. So it's a good idea. Try to dope with transition metals, for instance, these altermagnets. Thank you.
Thank you, Carlos. Great talk. So is your proposal that the altermagnets, the term is incorrect and you propose multiferroic materials, or is not in this direction?
Yeah, thanks, Gabriel, for the question. So the point here, Gabriel, is the following. It turns out that this term is not known in the literature. That's the point. So there is no any discussion, at least from the best of my knowledge, that comment this. So the main idea is to propose an explanation. I mean, what is the term that explains the spin splitting altermagnets? So I'm not saying that there is an incorrect view. I'm just saying that, okay, the spin splitting exists, and the point is, what is the physics behind this? So this is my proposal, let's say. I hope that this is correct, and I'm confident about this. Mera effect, this is the... But you know that in Brazil we use I have the two families' names, and my father's family name is Mera, and my mother is Acosta. Mera Acosta, yes.
Any other question? No, so let's thanks again, Carlos, for the talk. Okay, Fazio has one question, so...
To be clear, you said that just a minute, Maurice. Okay, thank you. You said that the explanation for that, they don't use this relativistic effect. That's right?
Correct.
Yeah. Then my question is, have you tried something like a dynamical Janteller, pseudo-Janteller, to I can explain from this?
That's a very good question. I would say that the first explanations that came out in the literature was actually related with the Janteller, the dynamic Janteller actually. But the point is the following: when you put this, in principle, you will need something like dynamic DFT or time-dependent DFT to explain the existence of the spin splitting. And it turns out that you just do a very naive DFT without the spin orbit coupling and without any time dependent, and you see the spin splitting. So the answer is not the best, yeah.
Okay, let's thanks again, Carlos, for the talk. Okay, so our next speaker is Mauricio De Cone. He's a professor here in Unicamp, very close by. And he's going to talk about mechanical and thermodynamic properties of water ice under extreme conditions. So thanks for coming, and the floor is yours.
All right. Good morning, everyone. First of all, I'd like to thank the organizers for inviting me. So I'm going to switch gears a little bit in terms of the type of system that's being discussed today. So I'm going to talk about water, specifically phases under extreme conditions of pressure and temperature. Well, as we all know, why do we study the systems we are looking at, right? Because we have to convince the funding agencies to, come across and give us money, right? I guess some of you have seen this already, but the most important thing is, of course, for technological reasons, to produce the perfect caipirinha, we need to know everything there is to know about ice. I think Professor Fazio knows very well about this, and I think this was some of the reasons that motivated, ice physics coming to Brazil. We're just kidding, of course. So water is really a fascinating system. In our daily experience, we only have, the vapor, the water, liquid, and the ice from the freezer. But if you look at different temperature and pressure conditions, the number of different phases you encounter is really astonishing. So On the left, there is this picture from the phase diagram, temperature on the horizontal axis, pressure on the vertical one. And you see all these Roman numerals. These are all different crystalline phases of water, right? This is actually taken from this site by Martin Chaplin, who basically maintains a record of everything that is known about ice, or water. So anything you want to know, just look at this site and you'll find it. And on the right, there is another picture of a phase diagram, which includes experimental data as well, by Milo in 2019. And you can see the temperatures are huge, right? 3000 K. Pressures are 300, 400 gigapascals. These pressures are of interest specifically, or one of the reasons is because of the planets Uranus and Neptune, which are known as the ice giants. And these planets are thought to consist in large part of these water phases at extremely high pressures and temperatures. And of course, basically the idea of this is, first of all, you want to know or gain a fundamental understanding of condensed phases of water in any case, so it's fundamental understanding, but also the role in the solar system and universe. And that's when these super ionic phases come into play. So this is just a cleaned up phase diagram. Again, pressure, temperature, and we have an insulating ice 10, super ionic ice 18, and we've got a conducting fluid. So this is, again, this phase diagram by Milo. And the white is the melting line. So what is superionic ice? Well, they only exist at high pressure, high temperature. So we're talking about pressures of 340 GPa, temperatures of the order 6,000 Kelvin. So you can imagine it's really hard to do experiments on these, right? So these experiments by Milo were actually shock wave experiments with in situ X-ray. So it's not something that you can actually statically create these phases, right? So, so what is that superionic ice? So there are no longer water molecules, right? So the oxygen ions form a lattice. So on the right you see this animation, ice 18. So the red spheres are the oxygen ions, and the whites are the protons. And a few of them are painted in blue just to show that they're just diffusing through like a liquid, right? So you could think of this as an inverted metal, right? Because a metal, you have positive ions and electron fluid, right? Here you have negative ions and a proton fluid, right? Okay. So this is another phase, ice 10 on the right. So the oxygens occupy a BCC lattice in this case, and the protons sit midway between the oxygens. So again, I've painted a few of those protons in blue. You can see that they no longer diffuse. So this is why this is called insulating, right? Because, so this is a metal, right? And this is an insulator, but not from the electronic point of view. So electrons do not matter here in a way. So the electrons are tightly bound to the oxygen ions, right? So why are these phases interesting from the point of view of objects in the universe, so specifically Uranus and Neptune. So these planets are the ice giants, and they have some really strange properties, specifically the magnetic fields. So this is a picture of Uranus and Uranus, Uranus and Neptune, actually. And for instance, Uranus, this is the rotation axis of the planet, and this is the magnetic axis. So they're really far apart. And in addition, you can see that this thing has shifted, right? So the magnetic poles. And something similar is going on in Neptune, right? So this was observed by the Voyager, Voyager 2. So one of the theories is that these anomalous magnetic fields are related to plastic flow of the superionic ices within the core of the planets. So our initial idea was, okay, let's see if we can understand some of this. So what we started out to do is try to look at mechanical behavior of these superionic ices. Of course, experiments are really hard to do, so that's a perfect place for atomistic simulations, right? DFT in principle is unfeasible because we need to consider large systems, right? So we use a neural network model to achieve this. And we look specifically at things like dislocation mobility and effective shear viscosity. I'm going to talk about this in a little bit more. So this was published in 2022 in PNAS. So how did we go about constructing the neural network model? So we used DeepMD-Kit, which is one of the popular platforms nowadays. As a training set, we used FCC and BCC crystals, the ones that I just showed you, 144 molecules at different stages of defect-free crystal deformation. I'm going to explain that in just a little bit. And different temperatures and densities, and fitted the model to DFT molecular dynamics data, PBE functional, CP2K, fitting total energies, forces, and stresses. So this neural network model is created specifically to describe mechanical properties of a bulk system. So what is defect-free deformation? It's something like it's related to this concept of ideal strength. So just imagine I have a perfect crystal, and initially there's no stress, so I have a stress-strain curve. Small stresses, what will happen is the stress will go up linearly as a function of strain. That's just linear elastic, because if you remove the stress, it will go back to the original state. If you apply a large stress, you'll start seeing non-linear elastic response. It will basically bend off, but still elastic, because if you remove the stress, it will go back to the initial state, right? Of course, at some point, the system will give, and you will see some kind of a rupture, okay? So these are snapshots from actual DFT MD simulations of this particular process. So this is our stress strain curve. We have these different letters here that correspond to different stages of deformation, right? So B is basically without deformation. C we're just starting to deform just a little bit, and we take the sequence on until, for instance, close to a G, the system has already nucleated a defect, which is a stacking fault in this case. Okay. So what we do is to train our model to reproduce these stress-strain curves. In practice, the deformation does not occur like this, right? Because there are no defect-free crystals, effectively. So the actual mechanism by which a crystalline solid deforms is called dislocation motion. And this is just a cartoon to show how to a crystal, you can cut a crystal and take the upper part and shear it with respect to the other. So that's the final situation here, but it doesn't occur all at once. So what happens is you introduce this defect and you propagate it through the system until it emerges on the other side. Effectively, you've then shifted the upper half with respect to the lower. Another way of seeing this is if you have a rug on the floor, you can push it at once, or you introduce a ripple and you propagate the ripple. That's the same effect. So this is a dislocation motion simulation in superionic ice with this model. So we used like 100,000 molecules for this. Well, there are no molecules, but H2O units. And what we found was extremely high mobility. That means it's really easy to deform this. And the viscosity was more than 10 orders of magnitude lower than people were thinking. So that was an interesting result from this particular studies. So you can see this is a dislocation running through the cell. So this model was constructed exclusively based on mechanical properties. So these stress-strain curves. Now the question is, can this model describe something else, or is it transferable, which is always an issue with these models, right? So we thought, well, what about thermodynamic properties? Can this model, which has not seen thermodynamic properties, can it describe those relatively closely? So that's when we come back to this phase diagram I showed earlier. And so we're going to consider these three phases. So the superionic ice 18, insulating ice 10, and the conducting fluid. Basically, we're looking at the phase transitions between these. So first, the melting transition. So we like to go from ice 18, which is this phase with oxygens occupying an FCC lattice and the protons flowing through like a liquid, to the conducting fluid, in which the entire system is fluid. So one thing you can do to estimate the melting point is, just starting here and then heating it up, right? That's a possible way of doing that. And the other transition that we look at is the one from ice 18 to ice 10. So this is the ice 10, so you can see this regular array for both subsystems, the protons as well as the oxygens. And again, this is ice 18. So here you could do the same thing. You can go heating it up from the BCC, or cooling down from ice 18. The problem with this, for instance, for the melting transition, if you just heat it up and wait for the system to melt, you have a problem of superheating, because it's a first order phase transition and you always have metastability or hysteresis, right? So to actually determine the melting point, thermodynamic melting point accurately, you need to compute free energies. Specifically for that transition, I need to compute the Gibbs free energy of ice 18 as a function of, or let's say the condition of coexistence is for the given pressure, at a given pressure, that at the melting point, the two Gibbs free energies should be the same. And the same goes for the ice 10 to ice 18 transition. Again, you either superheat or supercool in both cases. So again, you need free energies to actually determine the thermodynamic coexistence temperature. So how do we go about this? Well, there's lots of technical details which I will not go into because I don't have time for that. I could spend like a 2-week course on these methods. But the idea is that we use non-equilibrium thermodynamic integration. So it's a way of simulating a thermodynamic process in which you go from A to B in a reversible way. As we know that if a process is reversible, the free energy difference is equal to the work done, right? So that's basically the main concept here. We then first compute a single point free energy for at a given P0 and T0 using reference systems. So you go from the system of interest, which is ice 18 or ice 10 or the liquid, and switch it to a system for which the free energies are known. So that's one thing. Once we know the Gibbs free energy at a given point, we then extrapolate this as a function of temperature for the same pressure P0 using reversible scaling. So that will give us one coexistence point for the phase transition. And then the next thing, or the final thing to do, is we can actually extrapolate the entire curve in one shot by integrating the Clausius-Clapeyron equation, which tells you basically what the slope is of the coexistence curve, and you just integrate this. Okay. In this case, we all use classical MD because the effects of nuclear quantum effects have been shown to be very small for this kind of system. It's actually a paper from 2021 that showed that. We use a LAMMPS code with 1152 H2O units. So this is a result of the first single point calculation and the posterior extrapolation of temperature. So the pressure is 340 GPa. So on here I'm showing the Gibbs free energy as a function of temperature for the superionic liquid and ice 18. And so the red is ice 18, the blue is the superionic liquid, and where they crossed, that is what the melting temperature is at 340 GPa. Now, so in this case, we get 6459 K for this case. If I plot that in the phase diagram, it's pretty damn good, right? Because the white curve is the one that comes from the experiments from Milo et al. It's embarrassingly good agreement, I might say, right? Now, also that's an interesting thing to note here. I'm not sure if anyone notices, because just look at the character of the two curves. The slopes of them are almost the same, right? So this is a phase transition from a crystal to a liquid. And yet, the slopes of the two free energy curves are almost the same. Now, what does that mean? It means there's a very small latent heat for this transition. And the latent heat, of course, is related to the entropy difference. So the nice thing about these techniques, in which you get the curve as a whole, as a function of temperature, is I can numerically compute the derivative, and it'll give me the entropy. So here they are. These are the entropies of the, let's see, the red one is the liquid, and the blue is the solid. And the difference is 0.93 kb per H2O. And the absolute value of the entropy is about 22.5. So it's a really small difference. Now, where does this come from? So what we did was to do a relatively simple analysis. So we first tried to estimate something like an entropy of the liquid protons. So for that, we just use liquid theory, G of R. From G of R, you can compute the entropy. And if you look at the liquid, the protons in the liquid and the protons in ice 18, the entropy is basically the same, right? So it's 0.04 kb difference, which is very small. Now, if you compute the G of R for the oxygens, what you can see is that there are very large amplitudes of oxygen ions in the solid. So the vibrations of the oxygens are very large. And you can actually put this kind of vibration into this empirical criterion by Lindemann, the melting criterion by Lindemann from 1910, which relates mean square displacement with respect to equilibrium site to first nearest neighbor distance, right? So it's this delta L in which you divide the square root of the mean square displacement by the interatomic distance between the O. So there's this paper from 2020 which has computed this parameter at the melting temperature for a whole bunch of different materials, a whole bunch of different solids. And you get different values between like 0.07 to 0.13 or 0.14. So in this case, if we do the calculation, you get a number that's larger than anything that has been registered before. So the small difference in the entropy between contributions in liquid and a crystal are these huge vibrations of the oxygens. So even if you look at some of the snapshots, the disorder is pretty large. So it is in the liquid because it's vibrating in turn around stable equilibrium positions, but still it explores a very large region of phase space, which explains the small entropy difference. Okay. Now, let's go back to the phase diagram. So we had this initial red point, which was our initial estimate for the melting point. And the blue curve that you see here is the one that we get by integrating the Clausius-Clapeyron equation. Again, embarrassingly good agreement, I would say. right? So this was surprising to us that it's so good because we did not put any thermodynamic information into the model, right? The only thing we did was take stress strain curves and reproduce stress strains for different states of deformation. Now, this other transition. So ICE 18 to ICE 10. So on the left, we have just energy per H2O as a function of temperature. So this is just showing a hysteresis loop. We don't have a hysteresis loop for the liquid to the solid or solid liquid because I can go from the solid to the liquid, but cooling down for it to crystallize is really hard to do, right? So you can't really observe it within your simulation timescales. Here it's quite different. So if we start off at this is again 340 GPa. So if you start off at 2700 and you cool down, you see an abrupt transition. We cool down further, and then we move back up again, and it will go back to the perfect crystal. So on the right, you can see this transition occurring. And here we separate the visualization. On the left, we're showing only the oxygens, and on the right, it's only the protons. So the green is FCC, the blue is BCC. And you can see on the right, so this is a fluid, right? And once the transition occurs, you can see there is ordering immediately. So the proton subsystem has crystallized. So what's going on here? You are having a phase transition in which the oxygens go from one crystal lattice to the other, and the protons go from a liquid to a solid. So that means you have simultaneously two kinds of transition involved. Martensitic transition, which is something you see in iron, for instance, and a diffusive transition, which is crystallization. So this is quite uncommon. So here we again do the same thing. So we compute the Gibbs free energy as a function of temperature at 340 for both systems, ICE 10 and ICE 18. Where they cross, that's what the melting temperature or the transition temperature should be. If I plot it in the hysteresis loop, it's right in the middle, as it should be, of course. So that gives us the red dot here. And the blue curve gives us the coexistence line. I did not yet include the curve on the other side. So it's also a pretty good result. The dashed line is actually coming from DFT MD simulations. All right. So the question that we asked, so is the model that's developed only for mechanical behavior, is it transferable to describe something else? Well, apparently the answer is yes, and I don't know the reason why it is, if this is only a specific case, but of course this is a pretty nice result. Now, something else here. The kinetics, specifically of this ICE 18 to ICE 10 transition, because I was saying we have simultaneously two kinds of transitions going on. One, the oxygens going from FCC to BCC, and the protons going from a liquid to an FCC lattice. So what we did here is to look at atomistic snapshots in this region, exactly at the point where one goes to the other, just before and just after. So so I have the sequence of snapshots. So the top corresponds only to the oxygens, and the bottom are the protons. And so we can see it starts out green. At the third, at the fourth, you see some BCC showing up, and then it has completely transformed into a BCC. Now, if you look at the protons, you can see that it is disordered in the first one. In the second one, you can start seeing some kind of ordering happening. This order increases in the third snapshot, and in the fourth, it has almost entirely ordered already. And at the final moment, having complete order, basically. So we can see that the ordering in the proton system occurs before. So it seems as if first the protons order, and this then induces the transition of the oxygens. Okay, so this is still incomplete, so we're still working on that. But that's the thing that we think is going on at the moment. Okay, so that was basically what I wanted to talk about today. So this DP model transferability issue, so it is actually able to describe the phase transition, so the phase coexistence lines of the system for a DP model that was fitted only to mechanical properties. The proton crystallization occurs before the martensitic transformation in the ice 18 to ice 10. The melting transition has a very low latent heat, much lower than is typical for a crystal to liquid transition. And free energy calculations, the non-equilibrium approach is highly efficient. And I should also, of course, acknowledge the people that actually did this. So Milagros Raimundo is a student from Argentina. So she's going to MIT, and she got her interview at the embassy for July 10 to get a visa in the US. So that's great news. Vitor is making money at the bank now. Felipe Matusalem is a professor at ITA. Carlos Huest is in Spain, in Madrid, and Samuel is in Trieste as a postdoc. And with that, I'll be happy to take any questions you may have.
Thank you, Maurice, for the talk. So we have time for questions. So first, Joe, and then you talk. Yeah. You can go. Yeah.
Oh, first of all, thanks for the talk. I got a bit confused when you said that you only trained this model on mechanical properties. So what you're saying is that you only train the potential using, I don't know, virials or?
Yeah, basically, so total energies, forces, and stresses.
Oh, okay. So you also included energies and forces to
yes, of course. You need to do that because otherwise you will not be able to do any MD simulation. Okay. Right? So if you don't reproduce forces, you get this problem.
Okay. Oh, that's all. Thank you very much.
Hi, Christoph, MPSD Hamburg. So I wanted to ask about this BCC insulating phase.
Yeah.
So you form these clumps of protons, right? My question is whether there is always the same number of them or if they differ between different sites, and if they differ, whether there is some like larger BCC symmetry that they follow.
No, so as far as we can tell, the number of protons remains the same. So between each nearest neighbor oxygen pair, there's one. But the vibrations of the protons are really large. So when you look at these blobs, you see everything going up because you're actually looking along a line, right? So it seems as if there's a blob, but there's always the same number of, although I have to say, you can also create a BCC superionic phase. So, but that's at different conditions of pressure. And in those conditions, at some point, you can actually start have a diffusion from protons hopping to from one place to the other, and eventually become superionic as well. So, yeah.
Thanks.
Thank you for the talk, Maurice. I have two small questions. The first one, what is the main idea for not having nuclear quantum effects? You have very different proton configurations. And the second one, why would you expect that only training on mechanical properties would fail? Because locally you have all these different environments included. So what could be the failures that you expect?
Well, first of all, the quantum effects. So this paper I mentioned from 2021 makes a comparison between free energy differences using classical simulations and quantum simulations. The two plots are basically the same. I can show you the figure, right? So in terms of the free energies, the nuclear quantum effects seem to have a very small effect. The other, because stress is a global thing, right? So there's no way you can, include entropies or something like that, and that's a key element to describing thermodynamic properties. So the mechanical property, the only thing that we're fitting is we're just deforming a crystal, right, and make sure that it reproduces the stress that's induced in the system, right? And the systems that we'll look at to compute the thermodynamic properties are not deformed systems. It's just, the crystal, right? So that's what it is.
Okay, thank you.
Okay, Maurice, thank you for the nice talk. My question is, the series, you have a line from extreme condition, and you can get this condition. Have you applied some project to do the experimental here?
No. Well, I didn't even know it existed. So
I think the temperature you can get it from, I think it's 7,000, and the pressure higher than 6 gigapascal. Okay, Ben.
6 gigapascal is not
6,000.
Oh, 6,000. Okay.
I don't know how to do that.
600. Okay.
Sorry, 600 is possible to do this.
Okay. Well, that's interesting. Yeah.
Too close.
Yeah.
And the other question is more ingenuous question, and you don't have the contribution paramagnetic things in your entropy.
No, I don't think so. Where would it come from?
From the oxygen. You have the protons glowing, then that appears the magnetic moment. I don't know.
Yeah. Well, we haven't really looked into this, so yeah.
Thanks, Maurice. That's really interesting, the question. So just coming back indeed to the nuclear quantum effects, I know the paper of Bincheng, I actually looked it up again. And as you say, the temperatures are very, very high. So that's one reason why nuclear quantum effects can be small, even though the pressures are also high and so on. And they show that the free energies indeed seem the same. And that must have to do with something like the entropic contributions must be essentially classical to these type of things. But I wonder, and I don't know if you know, because when you have the superionic phase, you have also proton conductivity.
Yes.
And I could imagine that in proton conductivity, even at these, then nuclear quantum effects could have an impact. But are there measurements of the conductivity of protons at these phases, or is it known what it is?
I think the initial experimental observations of ICE 18, which, if I'm not mistaken, are from 2018, they did measure something like protonic conductivity. Actually, that was what they did to reach the conclusion that this was a superionic phase, right? Because there was conduction, right? But about the quantum effects, I wouldn't know, but
just if the measurements are there,
yes,
yes.
Yes.
Because calculating is very difficult.
Yeah, I know, I know, but yeah.
Any other question, Alexandre? Alexandre over there.
Thank you, Maurice. Could you comment a little bit about the fact that your transition temperature is spot on, considering that you have this interplay between nuclear quantum effects in other phase transitions of water, and also even the functional that is used. I mean, can also influence the phase transition.
Yeah. Well, to be honest, I don't know why. So like I said, it's almost embarrassingly good agreement from the result. So when we got the result, we were really, really surprised about this. And even if you look at just the coexistence curve, it's also very close. So I don't know. I mean, if we would have used a different functional, I'm not sure to what extent the results would be different. I mean, we could redo the entire scheme, run the DFT calculations again, doing the same scheme with deformation and everything, and look at the network model and do the calculations again, right? Now, another thing, of course, is look at the scales, right? Because that's maybe. So if you look at the scale, well, I mean, typically, if you compute like melting temperatures of like silicon, people look at 20K difference of temperature. Look at the scales here. We're looking at 6,000 K. So on this plot, it looks good, and also this white band is pretty large. So I think the result is as good as it gets. In this plot, it may look better than it should be, and also the white is only a crude estimate as well, because the experiments are really hard to do, right? So I think the message is we are pretty close, or at least in the right ballpark, within 10-20%, right? So I guess that's the thing.
Any other question?
Thank you very much for your talk. I'm Jorge from MPC Hamburg. You mentioned that the non-equilibrium free energy calculations are very efficient, and I was wondering, could you elaborate on how their efficiency compares with other methods like thermodynamic integration? Like in your particular system, why would you prefer to do non-equilibrium free energy calculations than any other method available?
I always prefer to use non-equilibrium simulations. Well, why are they more efficient? So thermodynamic integration, there is a number of issues. So one is you always have to pick your points. So you have lambda going from 0 to 1 or something. You have to pick the number of lambda values where you place them. Then you need to equilibrate them, do the averaging, and integrate them. All right. In non-equilibrium, what you do is you do a process in which lambda varies dynamically during a simulation. So you go from lambda 0 to 1 in a dynamic simulation. And the thing is, you can really observe the convergence of the result as a function of how quickly you do this process by combining going from A to B and B to A. Because the systematic error entropy production, because it's a non-equilibrium process, is the same in both directions if you are within linear response theory. So, for many different applications, you can converge the free energy difference using simulations of like 20 picoseconds. Okay. Typically, thermodynamic integration, you would run 20 picoseconds for just to equilibrate the system, right? So you have a systematic way of determining your error, and it tells you how long you have to go to converge, and that's something thermodynamic integration does not tell you, right? So in that sense, it's much more efficient.
Any other question? No, so let's thanks again, Maurice, for the talk. So this was the last talk. I want to thank Mariana, James, and Fazio for the organization of all the conference. I heard yesterday night that the next one is going to be in a few years in Cambridge. That's what Mariana promised us last night. So for all of you, probably we're going to see 2:30 p.m. for the INCT meeting, and for the other ones that are leaving, thanks for coming, and that's it.